Hello everybody. In this session, we are going to discuss the construction of control charts for variables. The total lecture is subdivided into 7 subheadings. 1. Data and necessary statistical computation. 2. General model for control limits. 3. Construction of limits for X bar, R and S chart. 4. Steps in constructing X bar chart, R chart or S chart. 5. Interpretation of X bar and R chart. 6. Table of constants. 7. Conclusion. First we will see how the data is tabulated and what all the necessary statistical computations are. Let us assume that there are k samples of size n each taken with observations x1, x2, etc. xn. The collected sample information will form the data set as given below. The table explains there are k subgroups. Each subgroup has n observations. For example, the first subgroup has the observations x11, x12, x13, etc. x1n. The second subgroup has the observations x21, x22, x23, etc. x2n. So, etc. there are k subgroups. For each subgroup, compute the mean. For example, for the first subgroup, the mean is x1 bar. The second subgroup, the mean is x2 bar, etc. Compute the range. For the first subgroup, the range is R1. For the second subgroup, the range is R2, etc. Compute standard deviation. The first subgroup, standard deviation S1. For the second subgroup, the standard deviation S2, etc. For all the k subgroups, compute mean, range and standard deviation. Calculate the overall process average. So, overall process average is mean of the subgroup means. So, x double bar equal to x1 bar plus x2 bar, etc. plus xk bar divided by k, where xi bar is the average of each subgroup. Estimation of sigma using sample ranges. From the sampling distribution of sample range R, it can be derived that expected value of R is equal to D2 sigma and standard error of R is equal to D3 sigma, where D2 and D3 are some constants depending upon the sample size n. The constants D2 and D3 are obtained based on the approximate relationship in finding the expected value of R in the distribution of R, as the distribution of R depends on n, the sample size. Hence, an estimate of sigma using sample ranges can be computed as sigma hat is equal to R bar by D2, where R bar is calculated as R bar is equal to R1 plus R2, etc. plus Rk divided by k, nothing but the mean of the ranges of different subgroups, where the range is computed as maximum observation minus minimum observation. Estimation of sigma using sample standard deviation. From the sampling distribution of sample standard deviation, yes, it can be derived that expected value of S is equal to C2 sigma and standard error of S is equal to C3 sigma, where C2 and C3 are constants depending upon the sample size n. The constants C2 and C3 are obtained based on the approximate relationship in finding the expected value of S in the distribution of S, as the distribution of S depends on n, the sample size. Hence, an estimate of sigma using sample standard deviation can be computed as sigma hat is equal to S bar by C2, where S bar is calculated as S bar is equal to S1 plus S2, etc. xk divided by k, which is nothing but the mean of the standard deviations of different subgroups, where the standard deviation of each subgroup is calculated as S square is equal to summation I is equal to 1 to n xi minus x bar whole square whole divided by n minus 1. Let T be any statistic that measures some quality characteristic of interest. Suppose that the mean of T is equal to mu T and the standard deviation of T is sigma T, then the general model of control limits are given by upper control limit is mu T plus 3 sigma T, central line is mu T, lower control limit is mu T minus 3 sigma T. Types of control charts. The control charts are classified depending upon the nature of the quality parameters like length, resistance, diameter, etc., and some non-measurable characteristics like good or bad, percentage of non-conforming units, number of non-conformities, etc. The control charts are classified as variable control charts and attribute control charts. Control charts for variables. Measurements on any quality characteristic from a process working under a system of chance causes are expected to follow normal distribution. About 99.73% of the observations from a normal population with average mu and standard deviation sigma fall within mu plus or minus 3 sigma. This knowledge is used to establish control limits at plus or minus 3 sigma from the central value of the process, representing the central line. Successive observations from this process can be plotted on a chart containing a central line mu, the control limits mu plus 3 sigma and mu minus 3 sigma. Any observation falling outside the limit is very unlikely when only chance causes are operating on the process, having a probability of 0.0027. Hence, an event of this kind indicates presence of assignable causes. Construction of limit for x bar, r and S chart. The control chart for the process average is x bar chart. With the data set defined as above, the control limits for x bar chart are established as from the general model of control limits. Let T denote the process average observed by sample means denoted as xi bar at regular intervals of time. Then the upper control limit is given by mu T plus 3 sigma T, that can be written as mu plus 3 sigma by root n, since expected value of x bar is equal to mu and standard deviation of x bar equal to sigma by root n. The central line can be written as expected value of x bar is equal to mu. The lower control limit can be written as mu T minus 3 sigma T is equal to mu minus 3 sigma by root n, since expected value of x bar is equal to mu and the standard deviation of x bar is equal to sigma by root n. The control limits for x bar chart depends upon the parameters mu and sigma. Depending on whether mu and sigma are known or estimated from the samples taken from the process, the control limits will take different structures as discussed below. Case 1. When mu and sigma are known and are assumed to take the values mu and sigma. The upper control limit is mu plus 3 sigma by root n, central line is mu, lower control limit is mu minus 3 sigma by root n. It can be also written as the upper control limit is equal to mu plus a sigma, central line is equal to mu, lower control limit is equal to mu minus a sigma, where the constant a is given by 3 by root n. All the constants a is directly available from the tables of constants, so hence the formula for limits is reduced in terms of a. Case 2. When mu and sigma are unknown. In this case, mu is estimated by x double bar and sigma is estimated using the sample range as sigma hat is equal to r bar by d2. Then for the chart, the control limits are given by upper control limit is equal to x double bar plus 3 by root n r bar by d2. we are replacing sigma hat by its value r bar by d2, or we can simplify that as x double bar plus a2 r bar, because the constant a2 is readily available. The central line is x double bar, the lower control limit is x double bar minus 3 by root n r bar by d2. So, that is equal to x double bar minus a2 r bar, where the constant a2 is defined as 3 divided by d2 root n. It is available in the table for different values of n. Case 3, when mu and sigma are unknown. In this case, mu is estimated by x double bar and sigma is estimated using the sample standard deviation as sigma hat is equal to s bar by C2. Then for the x bar chart, the control limits are upper control limit is equal to x double bar plus 3 by root n s bar by C2, or it can be simplified as x double bar plus a1 s bar. Central line is x double bar, lower control limit is x double bar minus 3 by root n s bar by C2, or simplified as x double bar minus a1 s bar, where a1 is equal to 3 divided by C2 root n and is a constant tabulated for different values of n readily available from the table of constants. R chart. The R chart is used for control of process variability when the process dispersion is measured using ranges. If sample range is used to measure the process variability, then the control limits are given by upper control limit is equal to expected value of r plus 3 times standard error of r, central line is equal to expected value of r, lower control limit is equal to expected value of r minus 3 times standard error of r. From the sampling distribution of r, it is known that expected value of r is equal to d2 sigma and standard error of r is equal to d3 sigma. Accordingly, the control limits are simplified as case 1, sigma known. Upper control limit is given by d2 plus 3 d3 sigma, that is equal to d2 sigma, where d2 is equal to d2 plus 3 d3. The upper control limit is expected value of r, expected value of r is d2 sigma, standard error of r is d3 sigma, hence the upper control limit is written as d2 plus 3 d3 sigma, or it is still simplified as d2 sigma, where the constant d2 is given by d2 plus 3 d3. Central line is given by d2 sigma, lower control limit is d2 sigma minus 3 times d3 sigma, or simplified as d1 sigma, where the constant d1 is equal to d2 minus 3 d3. Case 2, sigma is unknown. When sigma is unknown, it is replaced by its estimate r bar by d2, then the control limits are given by upper control limit is equal to d2 plus 3 d3 and the estimate of sigma is r bar by d2, or it is simplified as d4 r bar. The central line is r bar and the lower control limit is d2 minus 3 d3 r bar by d2, or it is simplified as d3 r bar, where the constant d4 is equal to d2 plus 3 d3 by d2 and the constant d3 is equal to d2 minus 3 d3 by d2. Again the constants d3 and d2 are readily available from the table depending upon the subgroup size. Construction of S chart. The S chart is used for control of process variability when the process dispersion is measured using standard deviations. If the sample standard deviation is used to measure the process variability, the control limits are upper control limit is equal to expected value of S plus 3 times standard error of S, central line is expected value of S, lower control limit is equal to expected value of S minus 3 times standard error of S. From the sampling distribution of S, it is observed that expected value of S is equal to C2 sigma and standard error of S is equal to C3 sigma. Accordingly, the control limits are simplified as, in the case sigma is known, the upper control limit is C2 plus 3 C3 sigma, or it is simplified as B2 sigma, where B2 is C2 plus 3 C3. The central line is C2 sigma. The lower control limit is C2 sigma minus 3 C3 sigma, or it is simplified as B1 sigma, where B1 is equal to C2 minus 3 C3. Case 2, when sigma is unknown. When sigma is unknown, it is replaced by its estimate S bar by C2. Then the control limits are given by upper control limit is equal to C2 plus 3 C3 sigma. Replace the value of sigma as S bar by C2, hence that can be written as B4 S bar. The central line is given by C2 sigma and sigma is replaced by its estimate S bar by C2, hence the central line is given by S bar. The lower control limit is given by C2 minus 3 C3 sigma. Sigma is replaced by its estimate S bar by C2, hence it is simplified as B3 S bar, where B4 is equal to C2 plus 3 C3 divided by C2 and B3 is equal to C2 minus 3 C3 divided by C2. Again B3 and B4 are directly available from the table. The following steps explains the construction of X bar chart and R chart. Construction of S chart is similar to that of R chart. Step 1. Gather the data. Select the subgroup size n. Typical subgroup sizes are 4 to 5 generally. The concept of rational subgrouping should be considered. The objective is to minimize the amount of variation within a subgroup. This helps us to see the variations in the average chart more easily. Select the frequency with which the data will be collected. Data should be collected in the order in which they are generated. Select the number of subgroups k to be collected before control limits are calculated. For each subgroup, record the individuals' independent sample results as discussed in table 1. For each subgroup, calculate the subgroup average xi bar, the range Ri as shown in table 1. Step 2. Plot the data. Select the scales for the x and y axis for both the X bar chart and R chart. Calculate the control limits for X bar chart and R chart and draw the control lines in the graph. The UCL and LCL lines are drawn as dotted lines and the central line a thick line. Plot the subgroup ranges on the R chart and connect the consecutive points with a straight line. Plot the subgroup averages on the X bar chart and connect the consecutive points with a straight line. A typical X bar chart and R chart is given in the following figure. The first one is X bar chart, the below one is R chart. The dots are the subgroup averages in X bar chart and the dots are the ranges of subgroups in R chart. These subgroups averages are joined with straight lines, the R's are also joined with straight lines, and yellow line is a central line, two thick red lines are the upper control limit and lower control limit. Step 3 is interpretation of the chart. Using the control chart, the process changes and presence of assignable causes are observed and interpreted as detailed in table 2. Suppose if you observe in the graph one or more points beyond the UCL and LCL, it says that the process is out of control. Even if the values are within the control limits, it might show some non-random situations or the presence of assignable causes in the system. That is explained in the following. Suppose if you see in the graph 7 or more consecutive points above or below the central line. So, this indicates a shift of process average. 7 consecutive increasing or decreasing points. This also indicates out of control, that means presence of trend or tool varying problems. 2 out of 3 beyond 2 sigma limits on the same side of the central line, it gives a warning of out of control situation, possible shift in the process average. 4 out of 5 beyond 1 sigma limit on the same side of the central line, this is again gives a warning of out of control situation, possible shift in the process average. 10 out of 11 consecutive points on the same side of the central line, it also explains shift in process average, hence the situation is out of control. 12 out of 14 consecutive points on the same side of the central line, so it indicates shift in process average, so the situation is out of control. A series of points hugging the central line, so again out of control situation, so it might explain improper estimation of process average. A series of points hugging the control limits, again out of control situation, shift in the process average above the expected average or below the expected average. 14 consecutive points alternating up and down, sawtooth pattern. So, oscillating process average, proper setting of the average value is necessary. Any non-random pattern such as cyclical and any other random causes of variation have to be identified. Normally, they are due to improper estimation of the process average or machine fluctuations. So, all these things if you observe in the chart, it explains that the process average is out of control. So, you have to see what actually is causing the process. Interpretation of R chart. One or more points beyond the UCL, so explains out of control situation. 7 or more consecutive points above the central line, it indicates the shift in process dispersion to a higher level. 7 consecutive increasing points, it is again out of control situation, there may be presence of trend or tool wearing problem. 2 out of 3 beyond 2 sigma limits above the central line, this gives a warning of out of control situation, possible shift in the process dispersion. 4 out of 5 beyond 1 sigma limit above the central line, this gives a warning of out of control situation, possible shift in the process dispersion. 10 out of 11 consecutive points above the central line, it indicates shift in process dispersion, so the situation is out of control. 10 out of 11 consecutive points above the central line, so it indicates shift in process dispersion, so the situation is out of control. A series of points hugging the central line, so out of control situation, improper estimation of process dispersion is assumed. A series of points hugging the upper control limit, again out of control situation, shift in the process dispersion above the expected dispersion. 14 consecutive points alternating up and down, sawtooth pattern. Oscillating process dispersion, proper setting of the average value is necessary. Any non-random pattern such as cyclical and any other non-random causes of variation have to be identified. Normally, they are due to improper estimation of process average of machine or machine fluctuations. 7 or more consecutive points below the central line, 2 or of 3 beyond 2 sigma limits below the central line, 4 out of 5 beyond 1 sigma limit below the central line, 10 out of 10 consecutive points below the central line. All these indicates, unlike in X bar chart, these situations may mean improvement in the process variation. However, the same has to be made sure that the estimate of average process dispersion is valid and does not change over time. Interpretation of S chart is similar to R chart. Trial control limits and control limits. The trial control limits are control limits for analyzing the past data or at the initial stage of establishing control chart, calculated following the procedure explained above. They may require modification before extending them for application of future production and maintenance of a stable process. If the data points are within the control limits exhibiting a stable process, we assume the process is in control. These limits are used for future use. Otherwise, We revise the limits by looking at the out of control points. Samples for which the plotted values go outside the control limits are eliminated for calculating the revised limits. This procedure is continued until all the points are within the control limits or the procedure is free from any assignable cause in obtaining the final control limits. Set up chart for process dispersion before working for XBAR chart, as XBAR chart requires an estimate of variability from a stable process. If the variability is out of control, then XBAR chart is not useful. When XBAR chart requires a revision, only XBAR chart is revised and the chart for dispersion is not revised. This is due to the fact that XBAR and R chart are independently distributed. Why two control charts, XBAR chart and S charts together? XBAR chart monitors the between sample variability and S chart or R chart monitors the within sample variability. Hence, two charts are necessary to study the process control. Range chart indicates a change in the process variability and that of the average chart indicates a change or shift in the level of the process. Hence, two charts are constructed simultaneously to see whether the process is working in control or going out of control in terms of the process average and process dispersion. The next question arises is choice between S chart and R chart. When to use S chart and when to use R chart. If the subgroup sample size is small, usually between 2 to 6, R chart is appropriate. When the sample size is large, S chart is appropriate, because when the sample size is large, R is varying too much. Since the quality control unit is there in all the manufacturing industries, different constants computing is a tedious job and all the industries use this technique. So, ready-made tables are available. So, we can easily read the constants in the table. The first column explains the subgroup size, each subgroup how many samples you are taking. If you are taking the subgroup size as 2, refer the first row. If the subgroup size is 3, refer the second row. If subgroup size is 4, refer the third row, etc. All the constants A, A1, A2, C2, B1, B2, B3, B4, D2, D1, D2, D3, D4 are readily available. That is why all the formulas for control limits are written in terms of either A, A1, A2 or B1, B2, B3, B4 or D1, D2, D3, D4, that simplifies the computations. Conclusion. In this lecture, we discussed how to construct control charts for variables in different situations and how to interpret them. We discussed setting up trial and action limits for XBAR chart, S chart and R chart. The different ways of identifying out of control situations using control charts. Process in statistical control. When to leave the process alone and when to take corrective action. Thank you one and all.